All right, fourth example of one-dimensional motion here. A police radar's effective range is 1 kilometer, and your radar detector's range is 1.9 kilometers. You're going 110 kilometers an hour in a 70 kilometer an hour zone when the radar detector beeps. At what rate must you negatively accelerate to avoid a speeding ticket? So let's get a sketch of the scenario. You're driving along, and then at some point, your radar detector beeps, which tells you that there is a policeman with a radar gun 1.9 kilometers away from you. So it's always good to look for this keyword when the something in a problem, because that can give you a hint as to an easy origin. So I'm going to pick my origin here at 0 kilometers, and this is at the beep. So your radar detector beeps here. That means down here at 1.9 kilometers, there's the police with a radar gun. Now, the policeman's radar gun, it says, has an effective range of 1 kilometer. So 1 kilometer from the policeman, so probably right about here, is when he can detect you. So if he's 1.9 kilometers away and from you, and the effective range is 1 kilometer, then this must be 0.9 kilometers. So you have to slow down enough within this range in order not to get a ticket. If you aren't at least at 70 kilometers an hour by the time you hit this point right here, then you will enter the cop's range speeding, and you'll get a ticket. So let's look at this region. What do we know? Well, based on our choice of origin, we know our initial position is 0 kilometers. And we know that the problem asks at what rate must you negatively accelerate. So we want to end right here. We want to reach our goal of 70 kilometers an hour at the end of this 0.9 kilometer distance. So our final position is going to be 0.9 kilometers. What about our initial velocity? Well, our initial velocity we were given is 110 kilometers an hour. And we want our final velocity to be 70 kilometers an hour. We want to slow down that much. And what are we asked for? We're asked for the acceleration. So given these four things, we have to figure out how much we need to decelerate in order to not get a ticket. So with position and velocity fully fleshed out here, we can look at our kinematics to decide what we want. So preferably, we want one of the formulas that has both positions and both velocities. So the first one is this one. And we definitely have both positions and both velocities here. And then we could solve for time. That would be great, but that's not going to directly help us. We could then use the time and maybe plug it in here and solve for acceleration, but that's an extra step. We have our fourth equation here that includes both velocities, both positions, and then the only unknown is acceleration, which is exactly what we're looking for. So we're going to choose that equation. So v squared equals v naught squared plus 2a times x minus x naught. And we're trying to solve for acceleration. So I'm going to subtract v naught squared from both sides. And then I'm going to divide by 2 times x minus x naught. And that leaves us with a. That's going to give us our acceleration. So once I subtract, then I can divide by 2 times x minus x naught, and then I get a. So once we plug in our numbers, we get a equals, so let's see, a equals v squared. Final velocity squared was 70 squared. And I'll make a note real quick. Everything we have here is in terms of kilometers and hours. And if we're solving for acceleration, we just kind of keep that in mind. We didn't convert down to SI units of meters and seconds. So our acceleration is going to be in terms of kilometers and in terms of hours. We just got to be mindful of that. So we get 70 squared minus our initial was 110 squared divided by 2 times our final position was 0.9. Our initial position, because of our choice of origin, was 0. So we don't have to do anything there. So what does this give us? If we type all of this into a calculator, what we get is about negative 4,000 kilometers per hour squared. Kilometers per hour squared. Now, that's not an incredibly useful unit there. We don't really know, don't have a good intuition for what negative 4,000 kilometers per hour squared is. So now that we have our final answer, let's just do one conversion to get it in terms of meters per second squared. So instead of doing 3 individual conversions up here, we can just work with those since they're already in the same units, and then just do one final conversion here. So we want to get rid of the kilometers, and we want meters. And we know that there are 1,000 meters in 1 kilometer. Now we have hours squared, so we want to get rid of hours, and we want to get in terms of seconds in the denominator, but we want everything squared. We're dealing with acceleration. So we want to get rid of the hours squared and replace it with seconds squared, and we know there are 3,600 seconds in 1 hour. So if we run that conversion, we get that we need to accelerate at about negative 0.31. Negative 0.31 meters per second squared. That's our acceleration. That's our acceleration. And that makes a little more sense. We can picture that. So every second, I need to be going 0.31 meters per second slower than I was the previous second. So that's a little easier to wrap our head around. So to answer the problem exactly, it said, what rate must you negatively accelerate? Well, we must negatively accelerate at 0.31 meters per second squared.